Lifting and holding, turning and pressing. Without compressed air, there's no holding or moving. This form of energy is a must for industrial production. The problem is 97% of the energy used to produce compressed air is lost as waste heat. That's why Teamtechnik, a company that makes machines for the automotive, medical, and solar energy sectors, uses a special device to produce this form of energy. A compressor draws in fresh air. Here, an electric-powered auger compacts the medium. The compression creates heat. But unlike normal compressors, this one doesn't let the heat go to waste. The heated air flows into a heat exchanger, providing warmth to the company's heating system. The compressed air is then conducted into a steel container, where it's available for production according to need. This air compressor uses about 70% of the electrical energy input, compared to only about 3% for compressors that use no waste heat. The southern German company uses compressed air to power tools such as pneumatic screwdrivers and grinding pencils, among others. Only with the help of compressed air do these instruments reach the necessary torque. Because of this and other uses, the fluid energy form is distributed through extensive pipelines in many companies. The problem is loss due to leakage. Teamtechnik uses a special ultrasound microphone to track down leaks. The mic detects exact sources of the sounds made by air seeping out of tiny holes, sounds that are inaudible to the human ear. That way, the tiniest leaks in pipes and joints can be quickly found and repaired. There are further simple measures that help minimize loss. In many companies, several air compression systems work independently of each other. A simple valve can be used to turn off parts that aren't used during late shifts, extra shifts, or on weekends. That also prevents further leakage from those parts. Teamtechnik not only uses the fleeting form of energy for machine production, the company also uses compressed air to power its own machines, and it's taken on an important function in the use of gripping systems. For the operation of special vacuum grippers, vacuum air is made from compressed air. To reach a high level of efficiency, the company uses an energy-efficient vacuum ejector in its machines. The compressed air flows over a so-called Venturi injector. Here, it's accelerated to the speed of ultrasound, pulling along the surrounding air. That creates underpressure in the adjacent part of the ejector. A sensor continuously measures the pressure. As soon as the necessary underpressure is reached, the vacuum can grip a component part, such as a solar cell. If the pressure continues to sink, the stream of compressed air is interrupted by a valve, and a stop valve seals the area with the underpressure airtight. The gripper can hold the component part as long as needed, without more air flowing over the Venturi injector. That saves energy. If the component is released, the valves open a direct path for the compressed air to reach the gripper. That allows precise control over the gripping process down to the exact millisecond. The use of vacuum ejectors creates two advantages in our machines. First, we lower the amount of compressed air we use since the vacuum ejector shuts off when it reaches the necessary gripping power. The second advantage is that we avoid damaging the solar cells because of the precision we use in gripping them. The use of efficient technology not only helps to save energy, it also increases the quality of production for lifting and holding, as well as turning and pressing.
This air compressor consists of an electric motor that compresses air into a storage tank. The compressed air can be released at chosen pressure when required. How works an air compressor? What are the criteria for selecting a proper air compressor? Well, there exists a variety of different compressor types. Let's continue with an overview. Normally, the compressors used in the field of automation and workshops are the so-called positive displacement compressors. Here, pressure is excited when air is drawn in a chamber and the volume of this chamber is reduced. In this video, we want to confine ourselves to this type of compressors. Let's have a closer look at the reciprocating compressor. As the crankshaft turns, a piston reciprocates within the cylindrical housing. The inlet valve, also called suction valve, allows atmospheric air to enter the cylinder. This is done during a suction stroke of the cylinder. The outlet, or discharge valve, opens at high pressure during the compression strike. Air heats up when it is compressed. This is a problem of each compressor. The result is not only a less efficient compression cycle, but also to a real danger of explosion if any inflammatory substances, such as oil or lubricant, get contact with the overheated air and piston. Therefore, the compression of a single-stage compressor is limited to an output pressure of about 10 bars, or 145 psi. To achieve higher pressures, you would use a multi-step compressor. Here, a two-stage compressor is shown. The large piston builds the first stage. The air leaving the first stage can now be cooled before it enters into the second stage. With a two-stage compressor, you achieve pressures over 20 bars or 290 psi. Multi-stage compressors with high power also can use water cooling to avoid overheating. Based on its working principle, the reciprocating compressor delivers only pulsed compressed air. Therefore, this type of compressor is used in conjunction with a tank. However, the use of a tank offers the advantage that the compressor can be operated with a two-point controller, resulting in less energy consumption and wear. The diaphragm compressor belongs to the family of the piston compressors. Here, the suction chamber is sealed from the piston by a diaphragm. As an advantage, the compressed air in the compression chamber does not come in contact with the lubricated piston, and thus can be kept free of oil. The weak point of a diaphragm compressor, in general, is its membrane itself, since the elasticity is limited. You would use the diaphragm compressor, for example, in the food industry or to fill divers' bottles. A totally different working principle has the so-called rotary compressor, also named as vane compressor. The typical rotary compressor has a cylindrical housing. Adjustable rotary vanes with its center point on an offset drive shaft have contact with the housing. So when the shaft rotates, these vanes create chamber of variable sizes. Air is sucked into the largest chamber, being compressed, and leaves the compressor at the smallest chamber. Advantage here is in the pulsation-free flow, in contrast to piston compressors. Therefore, an air tank may be optional. In addition, these compressors are quiet and relatively insensitive to dirt. Typical applications are, for example, wastewater treatment, fish breeding aeration, dust collection, vacuum packing, and so on. Watch also our next videos.
It's an inevitable fact of life that energy prices will continue to rise as we progress further into this century. Countries, and ultimately factories around the world, will face ever more stringent targets for CO2 emissions reduction. So it's vital that we use energy as sparingly and efficiently as possible for the sake of both economy and the environment. Approximately 10% of all electricity used in industry is accounted for by compressed air systems, and it's a thermodynamic fact that around 94% of this energy gets converted to heat. Heat that we first pay to generate, then pay again to remove by powering cooling fans, whilst in other parts of the factory we pay yet again to generate more heat for hot water, heating systems and application processes. There has to be a more efficient way of using this energy. Well, there is. Under ideal circumstances, 94% of the heat energy generated by compressors can be recovered, and Compare's range of heat recovery systems can help in utilizing that energy which would otherwise just go to waste. The principle of heat recovery lies in transferring the heat of compression into a cooling medium and then transporting the medium to where the recovered heat can be made use of. Within a compressor, the heat, which is created by compressing the air, is absorbed by the cooling oil. The oil, which is now hot, is circulated by pressure and flows through the plate heat exchanger. The heat is then transferred to the incoming water supply, heating the water at the same time as cooling the oil. The hot water can then be delivered for any application where heated water is required, such as steam generators, washing processes, boilers, heating systems, and many more. Every degree that we raise the temperature of water needs to be paid for. So if we have a water supply that is already 60 degrees Celsius higher than the standard water supply temperature, that's 60 degrees of heating that we don't need to pay for again. Preheating water for your heating system, hot water supply, or for use in industrial processes such as steam generation can provide significant savings and pay for itself very quickly. Additional heat that isn't captured in the cooling oil radiates into the canopy and exits the canopy roof as hot air. This hot air would ordinarily go to waste, but by installing heat recovery ducting, the hot air can be diverted to a different part of the factory. You can even switch the air to be diverted outside during the summer if it is not required inside the building. Installing a Compare heat recovery system can be surprisingly cost-effective and could be one of the best decisions you make this.
Alright, so today we're going to be looking at the differences between a belt-driven air compressor and a direct drive air compressor. Both of these air compressors are available at Super Cheap Auto, with this being the older model. I will link below the newer version. However, these are very, very comparable in the sense that they are at the opposite ends of the spectrums. This is one of the highest end models they make. This is one of the lower end models that they make. So what are the differences? What do you get for the extra money? I believe this normally runs about $400 to $500. This one runs in the high hundreds. So quickly, we'll start off with just the size. Obviously, the belt-driven air compressors as a whole generally are a fair amount bigger because they have this huge belt-driven system. They're always boxed in like this to keep it safe. And then they usually are the more powerful option. So they have a much bigger motor, a much bigger pump, and a lot more features, normally a bigger tank as well. So this air compressor has a 40-litre tank. This one over here has a 20-litre. So as we can see, we've got one here, one little air filter for the intake for the air. Over here we have two plastic ones. The plastic ones are actually a little bit cheaper than the metal ones. Later down the road I might switch these out because they are a little bit cheaper. but it doesn't faze me too much. I haven't broken one, I haven't had an issue with it. So as far as the actual overall size, this air compressor is much smaller. Obviously I can lift this up quite easily, could put this in the back of a car, no problems at all. Whereas the big 40-litre belt-driven one here, I can't lift that up, and I value my back working. There is no way I'd be able to probably pick this up by one person. I believe on the box somewhere it read 50 kilos, which isn't heavy, but in this sort of form where you've got to lean over the top of it, you can't really lift it up without lifting with your back, which is not advised because you're most likely going to hurt something. So as far as turning these on, same thing, little red switch, pull it up, air compressor begins, off we go. On the both air compressors, we have a release valve. I've got a little lanyard on this one so I can pull it much easier because this is the one I use all the time. So we use that, let go, pulls the air out. I think there's probably like a little bit of air in it. I was using this earlier today for brad nails. As well as that, for the valve on the end here, we both have a variable valve here, which allows us to adjust the output pressure, because I know sort of air impacts like about 90 PSI, and these charge up to about 115 each. So we can turn down the valves on this down to 90. So we can always make sure our air ratchets have the right PSI going into them. As well as that, something that this one has the edge on is it has two outlets like this. That way we can output to two air tools at once, whereas on the cheaper model, we can only output to one at a time. The cheaper model also has a cutoff valve here, whereas this unit over here doesn't have. I don't know if that's a feature that we'd actually use a lot. I don't think I've ever used that. Nonetheless though, unless I had a leaking air tool, which I definitely had with this one, got really, really abused, one of those air blowers. It got really abused, started leaking, so be it. So that's basically the difference as far as the build, the overall look. This is much, much smaller, much more practical, much more convenient, whereas this one is a lot bigger. So another difference with belt-driven air compressors is the noise. They make a fairly different noise, which isn't actually that much quieter as far as the overall volume. If anything, it's very similar. However, the tone of it is very, very, like much, much better to our ears to listen to. So what I'll do is I've got a decibel meter here. What I'll do is I'll run this one for a little bit. I'll run this one for a little bit. We'll measure what the average reading here is for the decibels. I don't think this decibel meter is very accurate, so don't take the numbers off this. But what you can do with the numbers you get off this is compare the differences. So that's what I like to use this for. It's not very accurate, but it's able to make a comparison between the two. So what we'll do, we'll start with our direct drive over here and we'll see what sort of decibel reading we get on here. So the decibel reading we got over here was 85.6 decibels. So now we'll start up the belt-driven one. And our belt-driven one is giving us 80.7. So we can hear 6 decibels quieter over the spectrum roughly there, just rounding a little bit, which to the human ear is actually half as loud. So it's definitely much quieter, but with that also being said, the actual sound, the tone of it is much, much better to the ear. Having one of these running is much, much better than having one of these running. And also with this belt-driven motor, it's delivering 185 litres per minute, which is a very, very large amount of literage per minute. This is able to fill the 40-litre tank in about 1.5 minutes, which is very, very quick. Whereas this one over here is only able to deliver 95 litres per minute, and it fills that little 20-litre tank in a couple of minutes, which to the ear sounds like a lot longer because it's a lot louder and a lot more painful to listen to. But there we have it. We just have a quick video here, a comparison between a belt-driven air compressor and a direct drive air compressor. The belt-driven is obviously much more powerful, much more quiet. Considering, like, the reason I wanted to compare these as far as volume is this is a base model direct drive and this is a fairly high-end, nearly top of the line belt-driven one, and it's much quieter. So you wouldn't think that the more powerful motor would actually be quieter, but it is. So that's really what I wanted to show you. So we have there a comparison between a direct drive and a belt drive. If you guys have enjoyed this video and have learned something from it and or want to go and pick up one of these, I'll link it down in the video description for you. With that being said though, subscribe to this channel if you haven't already, because I'll be doing plenty more videos with this air compressor and the tools that you can use with it. With that being said, I hope you enjoyed this one and I'll catch you guys in the next video.